Okay. Yeah, so the first question I will answer is what is a Lie group and what is Lie algebra? So what's the difference between the Lie group and the group? And what's the difference between Lie algebra and the algebra? Right. The second question I would like to answer is what's the relation between the Lie group and the Lie algebra? So basically how we go from the group to the algebra and how we go from the algebra to the group. The third question I want to answer is the representation theory of the Lie group, and I will use the SO3 and SU2 as an example because they corresponding to the spin, right? The different representation of SU2 corresponding to different spins. That's the most relevant group for physics. And if we have time, we'll talk about the SO4 because last time we talked about the hidden symmetry, the SO4 in the hydrogen atom problem. Okay, so that's the stuff I want to say. I want to discuss today. Okay, so let's start with the first question. By the way, if I don't have time to cover all the topics I want to say, I will upload anyway. I will upload my notes onto CCLE, so you can take a look if you want. So let's start with the first question. Let's answer what is a group, and then we will answer what is a Lie group. We will see what's the difference. The group, there. I mean, if you open a group theory book, I'm pretty sure the first page is there will be a rigorous definition for group. Generally speaking, it's just a set of elements plus a structure we call group structure, right? So what is group structure? Group structure, there's a binary operation called yeah, it's map G to G cross G to G. Let's call this set as G, whatever. So basically, this operation satisfy um, several conditions. One is if G1, G2 are in this set, then G1 times G2 is also in this set. And also, there exists an identity element. It's defined by E times G equal to G times E equal to. It's very intuitive. And the last thing is like there exists inverse element for every element in the set. I mean, it looks abstract if you only look at this kind of rules. But if there is a, let's give you an example, you will see it's very intuitive. For example, SO2 in that rotation group in XY plane, right? So this just tells you, the first row just tells us rotate angle theta 1, and then I rotate angle theta 2. Um, the effect of those two rotation is rotate angle theta 1 plus theta angle theta 2, right? And this is also a group element. And obviously this is true for SO2 group. And the second row just tells there's an identity like theta equal to 0 and remain everything unchanged. And this the last row just tells us there is a inverse for any operation. So if I rotate the angle theta, there must exist um, minus theta corresponding to rotate in another direction, right? It's very natural for the definition of the globe.
So is this G inverse defined by like G star G inverse is E?
Yeah, exactly. So this G inverse is defined by G times G inverse equal to E, and this is okay. So it's also equal. It's defined in this way. Yeah, I don't want to make like the definition too rigorous because it's this is a physics class. You just get the intuition and then that's it.
And,
Because uh-huh.
and for this SO2, is those like the set corresponds to any
Rotation.
2D space, and the structure is like the combination of rotations.
Yeah, exactly. So this is a set of this SO2, right? And the theta is from 0 to 2 pi. So each element in this set is a 2 by 2 matrix. And you can verify this is true. Like all the three rows, all the three rows are satisfied by this um, set. And in this case, the multiplication is just a matrix multiplication.
Okay.
Yeah. Yeah, I mean, as a physics student, we should always kind of have some example in our mind, because this kind of abstract definition, after a long time, eventually you will forget. Um, so what? Okay, so this is this is group. By the way, there are actually two operations in this definition, in this group structure. If you uh, if you really want to be precise, one is this um, multiplication. This is a operation. It's a binary. It's G to G cross G to G, right? Give me two elements, and the output is one element. There's another operation which is the inverse. It's give me an element in the group. I will give you another element in the group, right? And what is unique group? There are many different equivalent definitions. I will give you several definitions that I think are most important and useful for us. So the first one is Lie group is a set plus group structure. So this part give us a group structure, give us a group, right? And we also need add a topological structure onto this topological and also differentiable structure. This just tells us we can do calculus on this group. Yeah. Basically, we can do differential and integration. So I will explain to you what I mean by that. And of course, we want those two structures to be compatible with each other. That means there are two operations. I'm giving you a very rigorous definition, relatively rigorous, but you will see what this means. To be compatible, we require those two maps to be to be differentiable or continuous and differentiable. Right? Yeah. So okay, so group structure. So you can say there's an extra structure compared with a group. In terms of physical, like a physical terminology, it's like a group that we can parameterize using a continuous variable. Then there's a Lie group. The parameter space is the manifold of this Lie group. For example, like the SO2 basically is a group that can be parameterized by a parameters alpha s, and the the possible values or the parameter space is what we call the manifold of this group, of this Lie group. So for example, SO2, like what I wrote down above. In this case, we can parameterize this group using a continuous variable theta, right? And the theta is from 0 to 2 pi. And we identify 0 with 2 pi, meaning that the possible value of theta is actually a circle, right? And in this case, we say, okay, the group manifold of SO2 is nothing but a circle. By the way, feel free to stop me. Otherwise, I just assume you guys understand what I'm saying.
So does this mean that every Lie group must be parameterized by a continuous variable?
Exactly. Yeah, that's good enough for physicists. I mean, as a mathematician, there may be other like topological groups. Yeah, that's too much for us. Basically, Lie group is just a continuous group, for like a very roughly speaking.
Is that why we use this word topological in this context? Because otherwise,
Right.
that's all we really mean.
Right. Topological basically means you can define a neighborhood, right? Define like open set, right? When you have open set, you can talk about continuous. And actually, Lie group has another structure called differential structure, meaning that you can do calculus. But for us, topological, when you have some topological structure, you can talk about continuous. You can always do kind of, it's always differentiable. I mean, yeah. So I would say Lie group is nothing but a group, but a continuous group. Yeah. And a fancy way to say it is like a Lie group is a group and it's also a manifold. Okay, so this is one example we are familiar with. Another example we're familiar with is the, what's the name? Translational group. So we know the translation element, so the transformation, this set can be represented using this kind of A or X. Like this, X is the whole real axis, meaning that the X measures how much you translate along the axis, right? So in this case, this is also a Lie group. And the parameter space in this case is the real axis. So we say the manifold of this group is just a 9. Yeah. And there you can see there's a difference. One, this guy is not bounded, so we call non-compact Lie group. And this is bounded and closed, so we say it's compact Lie group. Yeah. So
that could you explain what that group manifold, like in the picture you draw to right of it, means?
Which one? Like you
No,
translation forward.
the group manifold SO2 and the pictures you draw like with a circle or something.
Yeah, this is a manifold of the Lie group of this SO2. What's your question? Can you say it again?
Like, did you draw it a circle just to mean that it is finite, or is it meaning? Is there a meaning like why you draw this way?
So this is I draw the circle because each point on this circle stands for element in the group, right? Because this is a parameter space. This is the where the theta lives.
Oh, I see.
Yeah. Similarly, this axis is where the x, the parameter lives. So the parameter space. By the way, for this manifold, this terminology manifold, you can think of as higher dimensional surface and curves like that, on which you can do calculus, like you can do differential operation, you can do integration operation. So basically, locally it looks like Euclidean finite space, but globally it may be topologically non-trivial. For example, the most familiar case is the S2, the sphere in 3 dimensions, like our Earth, right? Locally, locally you can map onto an open set on R2, but globally you cannot do this. It's globally non-trivial.
Mm-hmm.
Yeah. So far, any questions? Okay, so if no question, I assume you understand what I'm saying here.
Gee, I have a quick question.
Sure.
Is defining the manifold like, therefore you've defined the group and vice versa?
No, manifold is an independent object. So so every time the starting point is a set. You add different structure, you get different objects. You add group structure, you get a group structure, you get a group. This set becomes a group. You add the topological structure, you get a topological space, but you add topological structure and also differential structure, you get a manifold. And now what I'm saying is if you have both structure, it's a Lie group. Yeah. Yeah, another way to view this Lie group is from the topological side. Basically, if my starting point is the manifold, we know that, for example, a circle is a manifold, a sphere, like a 2-dimensional sphere is a manifold, and of course, in generally speaking, Sn is a manifold. Let's say S3 is a manifold. Now the question is, you may ask, can I add group structure to all manifolds? The answer is no. We know the S1, we can add a group structure, and the Lie group, the corresponding Lie group is the SO2, right? Or U1, doesn't matter, they're the same. Yeah, because U1 is just a phase change. We can parameterize this group using this exponential I theta. Theta is from 0 to 2. You can say the manifold is virtual circle, right? This is the reason why we say they're the same. For three sphere, we can also add we can also add a group structure and make it a group, which is known as SU2 group. But there's no way to add a compatible group structure to a sphere. And this is I think there are some rules for the manifold to be able to add a compatible structure, group structure. Yeah. So any question about this part?
So these 3 manifolds are a circle, a 3-dimensional sphere, and a 4-dimensional sphere.
Oh, a circle is like a sphere in 2 dimension, right? Like sphere is a 2-dimensional sphere is a sphere in 3 dimension. 3 sphere is a sphere in 4 dimension.
Okay.
Yeah, it's x1 plus x2 equal to 1. This is x1 squared plus x2 squared plus x3 squared equal to 1. And the x4 squared. Okay, so what else I want to say? Yeah, the next thing I want to talk about is the Lie algebra. So let's start with what is an algebra. There's a similarly there's a rigorous definition in math, but for me, what I remember is first you have a set, and you add some structure, you get a vector space, and so the starting point is a vector space. So once you have a vector space, and if you add another bilinear operation, then this vector space become an algebra. Bilinear, I mean, like I assume the bilinear operation is written in this way. I assume I denote the vector space as a V. Bilinear is the V cross V, give us another V, right? Give the input is 2 elements in the vector space. The output is 1 element in the vector space. And the bilinear means like the standard, let's say V1 plus BV2, CV3, and DV4 equal to AC V1 V3 plus AD V1 V4 and plus, yeah, it's bilinear. And okay, so this is algebra. There are several examples, many examples we're familiar with. For example, the complex number. Complex number. In this case, the vector space is R2, right? And the bilinear operation is the multiplication for the complex numbers. You can easily verify this multiplication of the complex number is a bilinear operation. And another example is in R3, the vector space is R3, and the bilinear operation is a cross product. This also form algebra. And this is actually the algebra of the SU2 or the rotational group. Okay, so this is algebra. So what is Lie algebra? Lie algebra is nothing but algebra with a Lie bracket. Okay, so first it's an algebra. Remember, algebra is a vector space plus a bilinear operation. And the Lie algebra adds 2 more constraints to the bilinear operation. We require this bilinear operation to be antisymmetric, and also satisfy the Jacobi identity. Yeah, something like this, and plus the x y equal to 0. Yeah, this is if you have an algebra with the bilinear operation satisfying those 2 conditions, then this algebra is a Lie algebra. And this bilinear operation is called Lie bracket. It's just a new name. You don't need to remember this. So now now it's clear what's the difference. You have actual 2 constraints. And now a natural question to ask is, what's the relation between the Lie algebra and the Lie group? It seems mathematically speaking, you can define them separately, right? So it turns out they are kind of very closely related to each other. So far, is everything clear?
Can I ask one quick question?
Sorry.
What was it that you said you add to a set to get a vector space?
Oh, add some structure. Like add in inner product, I guess you need to define inner. There's many rows to make a set a vector space, right?
Okay.
Yeah. So basically, the what I want to stress is the starting point is the vector space. Of course, you can regard vector space as some structure added to a set, right? But yeah, point is it's a vector space add some with some bilinear operation, then it's algebra.
Okay, thanks.
Could you explain one more time the bilinear operation, like the specific examples that you went over for the different vector spaces?
Okay, sure. Yeah. For example, this is the algebra, and the vector space is R3. It's just you know real space, and the bilinear operation is a cross product. In this case, it form an algebra. Actually, it form a new algebra, but it's form algebra is easy to verify because let's assume the element in this vector space is v1, v2, generally speaking vi. Then it's easy to say v1 a plus b v2 cross product CV3 plus DV4. You can say it's bilinear operation, right? It's equal to ACV1 cross 3 plus ADV cross V4 and plus BC2. It's something like that. This is bilinear. And also your elements it's a vector space, so it's an algebra. Yeah, and this is also Lie algebra because the cross product is antisymmetric, right? So it's v1 cross v2 equal to minus v2 cross v1, and this cross product also satisfies the this Jacobi identity. It's like yeah, you can verify this very easily. I guess you also did this kind of exercise when you learn some mathematical methods class. Plus, you do the cycle and you get 0. Okay, so yeah, any other questions? Yeah, feel free to ask. Otherwise, yeah, it's a discussion for you guys. Okay, sounds good. So what's the next thing I want to say? Right, what's the relation? The relation. Okay, so I will give you the results first. Then I will try to explain to you without introducing much terminologies. To understand it rigorously, to understand relation rigorously, you need some more new concepts. But I don't want to bother you guys with too much concepts. So basically, from the Lie algebra, sorry, let's look at Lie group to Lie algebra. Oops. Remember, Lie group is a manifold, right? Oops. Let's see some manifolds, and each point in the manifold corresponding to an element in the group, right? So let's assume this point. Oops. Yeah. This point is the identity element. Then the algebra is nothing but the tangent plane of this Lie group at the identity. And the generators of this Lie algebra is the basis in this tangent plane. Remember, Lie algebra is a vector space, right? Very naturally, a tangent plane is a vector space. And remember, Lie algebra has another structure called Lie bracket, the bilinear operation. That comes from the group structure, as you will see later. And if I think this is the most useful picture you should you should have in your mind for this Lie group and Lie algebra.
Is there any specific, like anything specific with this I? You said
I is the identity element in the Lie group.
Well,
yeah.
Is it the E?
Yeah, the E. Yeah, you're right.
Okay.
Sorry.
Sorry, one more time. What the Lie algebra? What is the specific connection to this tangent plane at the identity element?
The algebra is a tangent plane.
It is the plane.
Yeah, exactly. Yeah,
okay.
It's a tangent plane. Remember, the algebra is a vector space first. A tangent plane is already a vector space.
Okay, and it's specifically at the identity element in the group.
Exactly. Yeah.
Is it too complicated to explain why it has to be the tangent plane at the identity element?
Okay, I will explain to you later.
Okay. Okay.
Yes. Okay. So rigorously, you need to introduce some new concepts. I don't want to do that. I would like to give you some intuition instead. That's the most important thing for us, right? So okay. So what's the thing I want to say? Yeah, we know if we have a function f(x), the tangent vector at some specific point is given by the derivative of this function at this point, right? We know that. Now, for group elements, from physics, we know it can be written in this way. Some sum over mu. This L is the generators of this group. Generators of this group. And X mu basically tells us how much we rotate or we translate along some direction or around some axis. If you think about the rotational group or translation group, right? Yeah. So as a physics student, the most the best thing we have when we learn math is the examples. Whenever we have some examples, we will always be able to gain some intuition that really helps. Okay, so now let's say we have a manifold. Now I ask you, what is L1? L1 can be obtained by taking a derivative of this guy at the identity. This tells us L1 is nothing but a tangent vector at the identity. Similarly, L2 is also a tangent vector, and L mu is, in general, L mu is a tangent vector at this identity, and the space spanned by these generators is nothing but a tangent plane, right? And remember the algebra, like what we learned in physics, like Li Lj equal to I h bar epsilon ij k h lk, and all the elements is from this tangent plane. And specifically the generators serve as the basis of this Lie algebra. And now you may ask, what is the Lie bracket? Where the Lie bracket come from? So now, so far, we only use the property that the Lie group is a manifold, right? We haven't talked about what the group structure can bring us, right? So let's look at the group structure. So if we have a group structure, we can talk about the multiplication. Basically, the imagine this guy is oops. the elements in the group, then we can calculate this guy, the product of those two elements, and using the, what's the name, like the Baker-Hausdorff formula, something like that. You can write it down. It's given by some I x plus y plus 2 I half times xy minus yx dot dot. You can say when you calculate this kind of group multiplication, naturally there's an element you need to evaluate. So doing the group multiplication is equivalent to evaluate xy minus yx. And we define this guy as the knee bracket. And it's according to this definition, it's easy to verify xy equal to minus yx. And also it satisfies the Jacobi identity. And in physics, we call this knee bracket as commutator. So you can say the manifold, the fact that the knee group is a manifold will give us the vector space. And the fact that knee group is a group structure, will give us a knee bracket. So combine those two together, we get a knee algebra. So remember, knee group first is a manifold. It's also a group. So manifold would give us the vector space. So far, we don't know what's the bilinear operation, but when we look at the group structure, we do the multiplication, naturally, it will induce a knee bracket or a bilinear operation. In this case, it's a commutator. And this is nothing but a knee algebra. Is it clear? Or any questions?
So could you explain again how when you write the equation about the generators, like the g of x?
Yeah.
Yeah, is that like this? So what is this? This g is like a function from g to g, right? From big G to big G. It's a generator.
You mean this guy? This guy is just a group element in the group, right?
It's just labeled by x mu, right? So it's not a function of x mu. X mu is like a label of this element, right?
Yeah, exactly, yeah.
So here x mu's are like the labels or the parameters of the Lie group, and the L's are the generator, which is defined as this way.
Yes, here, because I don't want to introduce too much concepts, so I utilize this expression we often used in physics. And
yeah, but I'm always confused about the statements about generators, because
generators just defined in this. Generator is nothing but the basis in the Lie group, sorry, in the Lie algebra. It's defined in this way.
Sorry, say it again. How is the generator?
Generators, mathematically speaking, generators are nothing but the basis of the Lie algebra.
But you write this equation to relate this to Lie group, right?
Exactly, yeah. So if you really ask very like hard questions, like a very rigorous questions, I would say this analogy is not that good. But what I want to say is like kind of what I want to do is kind of convey this kind of intuition to you guys. if you want to make it more precise, you need to look up more rigorous textbook.
So we just take this relationship as granted, right?
Yeah.
Okay.
Yeah, the point is, if we have this kind of expression, very naturally, this kind of generators are the tangent vector at the identity. And that would give us a vector space, a tangent plane. And combined with a group structure, which will give us a Lie bracket, we eventually the tangent plane becomes a Lie algebra. Any
Okay, so the vector space of Lie algebra and the Lie group and the manifold of Lie group is linked by this known equation, known relationship.
Right. That's what I'm going to say next. If we know Lie algebra, we get a Lie group. Nothing, we just take the exponential. Yeah, it's kind of a the reasoning is not that rigorous, but I think it's good enough for you guys to get the intuition. So so how we go from the algebra to a Lie group? So the algebra is nothing but a vector space with a bilinear operation, right? And so whenever you have a Lie algebra, you should ask what's the basis. In this case, in terms of physics, so what's the generators? We denote as L1, L2, L3, dot. And to get the Lie group, we only need to do this operation. Take the exponential. But as you know, this there are several groups may share the same Lie algebra, right? For example, I have SU2 Lie algebra, which is Lij equal to I epsilon IJK LK. The corresponding Lie group has two, right? SO3 or SU2. So this is very natural because without any group structure, if I only know the tangent vector of some curves, I have no idea what the curve looks like at other places. So here, what we're doing is like from some local information, we want to get the global information, right? Without the group structure, we have no way to do that. But with group structure, we can somehow almost do it. But you can say there's still some uncertainty, right? It may be SO3 or SU2. But if you add another constraint, a global constraint, there will be one-to-one correspondence. The constraint is if we assume the group manifold is simple connected, then the one-to-one correspondence is exact. So basically, if we assume the Lie group, so what I'm doing here is I know the Lie algebra. I want to ask you, what's the Lie group? In general, there may be several Lie groups corresponding to the Lie algebra. But if I add a constraint, let's say, if I only want a Lie group that is simple connected, then the Lie group is unique. Is it clear?
Could you define simple connected?
Okay, simple connected means you draw a circle in the manifold, it can shrink to a point. For example, a sphere is always simple connected. You draw an arbitrary circle, it can always shrink to one point. But like a torus is not simple connected, right? If you draw a circle like this, there's no way to shrink to a point. Yeah. And using the topological language is a fundamental group of this group is trivial, corresponding to is simple connected. But okay, let's forget about this. It's random. It's not that random. Yeah. And there's a name for this kind of specific group. It's called a universal covering group. Yeah, it's just a name. Okay, so you can say from Lie group, sorry, from Lie algebra to Lie group, if we add a constraint saying that this Lie group is simple connected, I just write in this way, means simple connected, then there's a one-to-one correspondence. This is amazing because, like what I said before, without this Lie, without this kind of group structure, we have no idea how to get the whole information from a local structure, right? But with this kind of group structure, we can do it. We can almost do it. And we can do it when we have this constraint. Questions?
So is the constraint that the group has to be simple connected always the constraint, or just one example of a constraint that would allow you to reconstruct the group?
Okay, so I think it's the most useful constraint. There may be, I don't know. Actually, I don't know the exact answer, but I think if you assume, for example, if you assume if you add some other constraints, maybe the Lie algebra has no corresponding Lie group, because that constraint is not good. But what I know is this constraint is always good. Basically, give me this constraint, then the algebra always give us a unique Lie group.
So does in the example of the SU2 or SO3 or SO2 groups, could you explain how this constraint allows us to reconstruct one of those groups from a given Lie algebra?
Sure. Yeah, I can do that. I can do that. Okay, the most non-trivial example is like this. Is this one, right? I guess.
Yeah. So what constraint would you impose to get SO3 out of SO3 group out of SU2 algebra?
Okay, so that is a good question. So basically, this is why we call it universal SU2 as a universal covering group. So all other groups that share the same Lie algebra with SU2 can be obtained by doing some operations on SU2. That means we really only care about this SU2 because other groups can be obtained by doing some operations on this group. And this is also universal covering because, okay, so as I'm pretty sure you know this relation. This is as a manifold, it's nothing. SU2 is a 3 sphere, and SO3 is a real projective plane, right? So let's visualize this this guy. How to do that? Even though I draw a sphere, but I assume this is a 3 sphere in 4 dimensions. There's no way to draw it, right? So I just assume it's 3 sphere. And modulo Z2, meaning that I identify the point G and the minus G. So they're the same point. If we know SO3, there's no way to recover this SU2. But if we know SU2, we can do this kind of identity of by identifying different points, we can obtain this SCO2. And we say it's a universal covering group because it's kind of a, in some sense, it's bigger than the other groups. And the SO2, SO3 is not simple connected. You can construct a loop that cannot shrink to a point. The loop is, for example, from minus G to G. This is a loop because G and minus G are identified as one point in this group, right? This is a loop, but this loop cannot shrink to a point. It's like if you move this point around, this point will also change. There's no way to shrink to a point. Yeah, the equivalent way to say this is the fundamental group of this guy is Z2. There is a non-trivial element. Yeah, actually, time goes very fast. I thought I can finish the representation part. That's the most important part I want to say. But turns out I only finished the first two parts. Yeah, this part, representation, unitary representation, and kind of related to spin 1, spin 2, spin 1/2, stuff like that. And also tensor product representation and the direct sum of representations. And yeah, I have no time to do that. But anyway, I will upload my notes onto CCLE, so you can take a look. And if you have any questions, just let me know. We can discuss during office hours or via email.
Maybe you would like to do that either like the next discussion or during your office hours, because I think like you actually talking through it is more helpful than just notes.
Okay, sure.
At least for me, I don't know the other field.
Okay, sure. Let me think about. Yeah, I can do next week if you guys want me to finish that. Yeah, I hope this helps, like some basic relations and. Yeah, there's also a group theory class, right, in physics department this quarter. I think so, right? Like the mathematical methods 2 or 1, 2, yeah, 2. GoPro is teaching that, I think. But yeah, definitely.
It's during quantum.
Sorry?
It's at the same time as quantum.
Oh,
it's not group theory this quarter. It's manifolds and other fun stuff.
I see. It's more topological side. I see. Interesting. Usually it will teach some group theory, like representations and stuff like that. Yeah, different professors may have different content. That's interesting. I see. It's the same time as quantum. Yeah, but anyway, I hope this give you a very brief idea what's the Lie group and the Lie algebra, and what's the relation. And yeah, next time we can talk about the representation, which is the most important part. Yeah, I think if we do it next time, I will have time to talk about the SON in general. And yeah. Okay, cool. So stop sharing. Yeah, any questions? If you have questions, you can stay. If you have no questions, you're free to go. Yeah, time is up.
Thanks, G. This was really helpful.
Thank you, G.
Thank you.
Appreciate it.
Mm-hmm.